This video looks at the idea of an orthonormal basis, and it looks at the process by which orthonormal basis vectors are created using the basis vectors derived from the tangent space of a manifold. So we've got a manifold, and we're looking at a coordinate transformation from x1, x2, x3 coordinates to y1, y2, y3. So we've got some manifold in 3 space. Position vector in the x-coordinate system will be this object here. Now the coordinate curves are given by varying y1 but holding y2 and y3 constant, and the next coordinate curve, the second one, is given by holding y1 constant, c1 here constant, varying y2 and keeping c3 constant. We've seen all this in a previous video, and the coordinate surfaces, like as was shown in the previous video, y1 is equal to a constant, y2 is equal to a constant, y3 is equal to a constant. We'll see some pictures of those in a moment. So a set of basis vectors at every point in the new coordinate system is found using the coordinate curves. So at every point on this manifold, we can form a set of basis vectors. We're in 3 space, so we'll form 3 of them. So our first coordinate curve is this one here. That's where we varied y1 but held y2 and y3 constant. The other coordinate curve is this one here. Y2 is varied, the others are held constant. And the third coordinate curve is this one here. And the y1, y2 are constant, and y3 is allowed to vary. Taking the derivative of these coordinate curves, we get dy. Taking the first derivative with respect to y1 gives us this tangent vector here. Second derivative, the derivative of the position vector with respect to y2 gives us this tangent vector here, and likewise the derivative with respect to y3 of the position vector gives us our third tangent vector here. And we can do this at every point in the space, or every point on the manifold, to get this set of mutually orthogonal basis vectors. And we've seen that in a previous video. Now these vectors lie in the tangent space of the manifold, and they form the covariant basis for the space. The reciprocal or dual basis is found using the coordinate curves of the manifold. So here we have y1 is set equal to a constant, and this surface here is formed by using the second coordinate curve and the third coordinate curve. Together, the surface lies in that direction. So a normal pointing out of that surface in a positive or anti-direction would be coming out this way in the direction of the first coordinate curve. So this is our first coordinate surface. There's not room to put the others in, otherwise the diagram would be very messy. But there's 2 other coordinate surfaces as well. And these vectors are known as a contravariant basis. That's these blue ones here. So we have a contravariant basis, one of which is shown here. The covariant basis in the tangent space is given by E1 as dr dy1, E2, E3. An orthonormal basis for this space, these are already orthogonal, as we showed in the previous video, but an orthonormal basis then is just taking the mod of these, dividing each vector by the mod, as you'd expect, the modulus of the vector, so we produce 3 of them here. Now, not only are these orthogonal to each other, but they are now also of unit magnitude or unit length. So in general form for n-dimensional space, we can compactly write this as this object here. These basis vectors can be shown to be of unit length, so the modulus of the basis vector, or the general expression for the basis vector, E subscript I, square root of E subscript I dot E subscript I, gives you this object here. It's dotted together with these 2 mods down here, moduluses down here. Separate the square root, numerator and denominator. This, by that, is squared, and the square root of it gives you this object here. Now, by definition, this is the modulus of the vector, dr dyi. That divided by that gives you 1. So we've seen now that these basis vectors are orthonormal because they are not only perpendicular, but they are also of magnitude 1. Right. The contravariant basis, or the dual or reciprocal basis, is given by these objects here, with the contravariant upper index. These are the basis vectors. And again, an orthonormal basis for this space is given by these objects here. or in general form, E contravariant or upper index I, this object here. This can be shown to be of unit length as well. We take the modulus again, follow the same process that we did before. Same definition, same process. This is a vector dotted with a vector. Square root of that gives you the modulus of the vector. This object here, two moduluses multiplied together, then square rooted. So it gives you a unit length. So each of these vectors is of unit length, and as we saw in the previous video, they are also mutually orthogonal. Alright, so an example now is consider a coordinate change on some manifold in 2 space. So we're going from Cartesian coordinates xy to polar coordinates rho and phi. Our coordinate transformations are x equals rho cos phi, y equals rho sin phi. With position vector in terms of rho and phi. There we are. Right, so our basis vector in new coordinates is given by e subscript rho as dr d rho. Just partial derivative of the vector with respect to rho gives us this object here. Now, this turns out to be our first orthonormal basis vector because the modulus of this vector is 1 anyway. So our first basis vector in our orthonormal basis, our first newly created orthonormal basis vector, e subscript rho hat, is just e rho. Our next basis vector, e subscript phi, is dr d phi. Differentiate the previous position vector with respect to phi, and we get this object here. We take its magnitude, gives us this object, which gives us rho. So the magnitude of this vector is not 1, so it's not a unit vector. So our second orthonormal basis vector then, e subscript phi hat, is 1 on rho e phi, and that will give us then a vector of unit length. So our orthonormal basis, we only need 2 of them, we're in 2 space, e rho hat, e phi hat, is these 2 vectors here. This object here is now of unit length, and so it's the second basis vector in our orthonormal set basis vectors. Next bit. So the covariant vectors of the tangent space TP are related to the contravariant vectors of the dual space TP star, as we in the following way, and we found this in the previous video. We showed why that's the case. Right, now for some given surface U is a function of y1, y2, y3, so we're back in 3 space again. It is equal to a constant. A normal vector to this surface is given by, and this is a general normal vector, not of unit length, just a normal vector to the surface. Any vector can be written in any vector that is can be written in either of the following 2 ways. It can be written with contravariant components and covariant basis vectors, or it can be written with covariant components and contravariant basis vectors. Alright, so unit normal to this surface is given by n hat is this object here, whereas this is an orthonormal basis vector. Now we can use the inverse metric here, gij, to raise this index, and we get del ju, this, or we could write it as del lowercase lower subscript I, u, and use the contravariant basis vectors. So here we use the covariant basis vectors, here we use the contravariant basis one. Notice they're orthonormal because we're using the hat, so they're of unit length each, and that object can be written as that. Now these vectors can be shown to be of unit magnitude or length in the following way. We can show this is of unit length or magnitude 1, so it's a unit normal vector. And to do that, we show this, modulus of n, square root of n hat dot n hat, gives us this object here. There we go, dotting that together. Now, let's take out this basis vector dotted with this basis vector over here. Otherwise everything else is the same. Now, Kronecker delta applies here, as we saw earlier, and in the previous video, the Kronecker delta applies. In that case, when j is equal to I, this j over here will become an I. We'll get this object multiplied by that one over this object. So put them together like that. Square them. Now, square root and square cancel out, so we're left with this object underneath. Now, whatever space we're in this case it happened to be 3 space, but whatever general space is, we're going to I would run from 1 to 3. The same here, n would also run from 1 to 3. So these two objects are the same as each other, and that they then cancel out, and and we're left with the square root of 1, which is just 1. And that shows that this normal vector here is a unit